Okay, I think it's time to start again. So our next speaker is Lucrezia Bottegoni, who will speak on semi-separable functors.
Thank you. Do you hear me? First of all, I would like to thank a lot all organizers, and in particular the scientific committee, for giving me the opportunity to talk at CT 2021. In this talk, I'll present a joint work with my supervisor, Professor Ardizzoni from University of Turin, about a weaker notion of separable functors that we call semi-separable. Just to give a motivation to our study, recall that whenever we have a functor, we can consider the associated natural transformation FF. And in particular, when this map is injective for any pair of objects X and Y, we have the notion of faithful functors. When this map is surjective, we have the notion of full functors. And moreover, if this map satisfies some good splitting properties that we'll recall in a moment, we have the notion of separable and naturally full functors. Now our question is there a notion that allows us to study at the same time separable and naturally full functors and extend their properties? The answer is yes, and in this talk, after recalling the basic results about separable and naturally full functors, we'll introduce our definition of a semi-separable functor, and then we'll see how they behave with respect to adjunctions. Finally, we'll consider some applications from ring theory. In particular, some applications from functors induced by ring morphism, co-rings, and by modules. Let's start with the definition of separable functor. This notion is due to Nastasiescu, Vandenberg, and Van Oysteyen in 1989, and a functor is said to be separable if the associated natural transformation F splits, which means that there is a natural transformation P such that Pf is the identity on the home C by functor. This condition can be translated on morphisms by this equality, and the fact that P is a natural transformation means that whenever this diagram is commutative, then also this diagram commutes. In particular, if we replace G with by the identity map on Fx, we can find that any separable functor is faithful. And moreover, if we take a morphism and a separable functor, if FF splits or co-splits through a morphism G in D, then also F splits or co-splits through PXYG. And as a consequence, separable functors satisfy a Maschke theorem, which says that a short exact sequence, which is split after we apply a separable functor, is itself split. The motivating example which led the author to introduce the notion of separable functors comes from ring theory. If we take a ring morphism from R to S, unital rings, and if we consider the extension and the restriction of a scalar's functor, we have an adjunction, and in particular, the extension is separable if and only if the map phi splits as an R bimodule map, which means that there is a map, an R bimodule map key such that key phi is the identity on R. And moreover, the restriction is separable if and only if the extension of S over R is separable, which means that the product map as an S bimodule section. This definition is compatible with the classical notion of separable algebra, and this is the reason why they called these functors separable. Moreover, we have a result from in 1990 from Raphael. Raphael is an acrostic for a group of people who study this topic in an algebra school in Cortona. If we take an adjunction with unit eta and the co-unit epsilon, we have that the left adjoint is separable if and only if the unit splits, whereas the right adjoint is separable if and only if the co-unit co-splits. In a sort of dual way, the notion of naturally full was introduced by Ardizzoni, Canefil, Menini, Militaru in 2006, and this time a functor is called naturally full if there is a natural transformation PF such that FP is the identity on the home DF by functor, and also this time this condition can be translated by these two equalities. And in particular, it is well known that a naturally full functor is full, and the notion of a fully faithful functor coincides with the notion of a separable functors that is in addition naturally full. Also this time we have a Raphael type theorem for adjunctions. In particular, the left adjoint is naturally full if and only if the unit co-splits, whereas the right adjoint is naturally full if and only if the co-unit splits. If we come back to our example, this time we have that the restriction of scalars functor is naturally full if and only if it is full, whereas the extension is naturally full if and only if there is a map key such that phi key is the identity on S. Now we are ready to introduce our definition of semi-separable functor. We say that a functor is semi-separable if there is a natural transformation P such that FPF is F. The first observation is the following. F is semi-separable if and only if there is also a natural transformation P prime such that satisfy this equality, which is exactly the first one, and also this equality. And this property explains the reason why we call this functor semi-separable, because this property is exactly the analog of the fact that in a semigroup theory, any regular element has an inverse. To prove this remark, one direction is trivial, the others, it is enough to set P prime as the composition of PFP. Now, the first step is to give a characterization of separable functors in terms of semi-separable functors. We have that a separable functor is a functor that is faithful and semi-separable. This follows by definition in one direction and also in the others by using the faithfulness of F. In a similar way, a naturally full functor is a functor that is semi-separable and full. The first difference to point out from separable and naturally full functor is the following. Separable and naturally full functor are closed under composition, but this is not true for semi-separable functors. In fact, we have this counterexample. If we take two morphisms of rings such that the first extension of scalars functor is separable, and the second is naturally, and the second extension of scalar functor is naturally full, we have that the composition of these two functors is not semi-separable in general. In fact, in particular, in this case, where phi is the map from Z to Q times Z, and psi is the projection on the first component, we have proved that this composition is not semi-separable. But to do so, we need some more results. In particular, a Raphael type theorem for a semi-separable functor. But even though this closeness is not well behaved for semi-separable functors, there are some special cases in which this closeness is satisfied. If we take two functors and if we consider the composite, if the first one is semi-separable and the second one is separable, then the composite is semi-separable. And also if the first one is naturally full and the second is semi-separable, then also the composite is semi-separable. This follows by a direct calculation, and in particular in both cases the composition is semi-separable with respect to PFPG. Just an example, if we take the canonical injection from rationals to the polynomial ring over rationals and the projection on the first component, we have that the induction functor phi star composed with psi star is semi-separable, but it is neither separable nor naturally full. The next step we are interested in is to characterize a semi-separable functor as the composition of a naturally full functor followed by a separable functor. And to do this, we need the construction of the co-identifier category, which is a category which has the same objects of a given category, and given also an idempotent category, an idempotent natural transformation, we have that the morphism of this co-identifier category is given by the class of morphism such that F is in the same class of G if and only if B F is equal to B G. And moreover, there exists a functor canonical from C to CE, which acts as the identity on object and as the canonical projection morphisms, which is moreover naturally full always through this natural transformation. And the second ingredient to characterize to characterize a semi-separable functor is given by the following proposition. In fact, if we have a semi-separable functor, there exists always an idempotent natural transformation E from the identity on the category C, such that Fe is the identity on the functor F, which satisfies, moreover, this universal property. And to prove this, we can set for any object x in C, Ex has the natural transformation Pf given by the semi-separability of F, evaluating in the identity on the identity Fx. And this and the following is the theorem about the factorization of a semi-separable functor. We take a semi-separable functor, and so we have seen that we can consider the associated idempotent natural transformation. Then there exists a unique Fe, a functor necessarily separable, such that F is the composition of H with Fe, and in particular, H is the canonical naturally full functor, and moreover, if F also factorizes as a separable functor and a naturally full functor, there exists a unique functor from C to E, which is moreover fully faithful, such that the two triangles commute. As a consequence, we have that any semi-separable functor can be factorized as a composition of a naturally full functor followed by a separable functor. And this follows for one direction by this theorem, and for the other direction by the lemma about the composition of semi-separable functors. Now we can pass to consider adjunctions. Also for semi-separable functor, we have a Raphael type theorem. In particular, the left adjoint is semi-separable if and only if there is a natural transformation Ni which satisfies these three equivalent conditions, and also dually for the right adjoint. And the first consequence of this result is given by the following. If we take an adjoint triple, then the left adjoint of G is semi-separable, or as a consequence separable and naturally full, if and only if so is H. And moreover, we can study semi-separable functors with respect to correflections and reflections, by which I mean a functor with a fully faithful left or right adjoint respectively, and our correflection is semi-separable if and only if it is naturally full. To prove the theorem, we give a sketch. In particular, the idea of the theorem is to construct a bijection between PF and the natural transformation Ni. In one direction, we define Ni X as the map PF evaluated in the counit Fx, and then doing calculations. And on the other hand, we define the natural transformation PF as the composition of Ni, GF, and eta X. As an application of our theory, we can consider the Heilenberg-Moore category associated to a monad and comonad for an adjunction. In particular, we have this diagram, and if we take the adjunction Fg, the right adjoint G results to be semi-separable if and only if the forgetful functor is separable, which is equivalent to say that the associated monad GFG epsilon F eta is separable, and the comparison functor is naturally full. And at the same time, G is semi-separable, and as a consequence, separable, naturally full, and fully faithful, if and only if so is the free functor, the co-free functor VFG. And this follows by the fact that these two adjunctions has the same associated comonad. And dually, we can state our result for the left adjoint. Now we'll see some application of our theory in ring theory. We come back to our example. We take a morphism of a ring from R to S, and we consider the extension and the restriction of scalar functors. And moreover, we can also consider the coinduction functors. And these three functors are an adjoint triple. So we have that the extension is semi-separable if and only if the coinduction is semi-separable by our previous corollary. And this is equivalent to say that there exists a map, an R bimodule map key, such that phi key phi is phi. In other words, phi key on the identity on the ring S is the identity on S. Moreover, if we take an epimorphism of rings, then phi star is semi-separable if and only if it is naturally full. And this is also an example of correflection and reflection. Moreover, from corings, I recall that an R coring, where R is a ring, is an R bimodule with two R bimodules maps, the comultiplications and the counit. We have, which satisfies these two equalities. we have that the induction functor from the category of right R modules and the category of right C comodules is semi-separable if and only if there is an invariant element in the center of C, such that this equality is satisfied. These equalities extend, in a sense, the well-known results for separable and naturally full functor. In fact, these two conditions for these functors are particular cases of our. And just an example, if we take a morphism of rings, we have, we take such that phi star is naturally full, then we can consider the Harco ring as delta key, where delta is the following, and the key is given by the naturally fullness of phi star. We have that the functor G is semi-separable through the identity on S. The last example is provided by modules. We say that an R-has bimodule is semi-separable if there is an element in the center of the tensor product of the dual of M and M, such that this element satisfies equality. And thanks to this definition, we can prove the following theorem, which says that a functor is semi-separable if and only if this functor is semi-separable if and only if the bimodules is semi-separable. This functor is the induction functor for bimodules. And as a consequence, this theorem allows us to characterize separable bimodules in terms of semi-separable bimodules and generator. We have that an R-has bimodule is separable if and only if M is semi-separable and M is a generator as right S module. Which means that this functor is faithful. Here are some bibliography for the study, and thank you very much for your attention.
Do we have any questions from the audience? Yeah.
Okay, so thank you for your interesting talk. You mentioned the Maschke theorem, which was one of the underlying motivations way back in 1989 when Van Ostaayer, Van den Berg, and Năstăsescu introduced the notion of separable functor. Is there something similar for semi-separable functors?
Yes, we have, sorry, I shared the screen again. No, okay, do you see? No, okay. Okay, the answer is yes. In fact, I don't know if you see. Okay. The answer is yes. In fact, by our definition, sorry, I come back. Okay. For semi-separable functors, there is always a unique idempotent natural transformation E, which satisfies this condition. And thanks to this natural transformation, we can prove another characterization of separable functors in terms of Maschke and the semi-separable functors. We have a characterization, and a separable functor, a functor is separable if and only if it is semi-separable and Maschke. By Maschke, I mean that it reflects split monomorphism.
Yes.
I don't know if I answered the question.
He says yes. Hi, thanks for a really nice talk. I've been a little bit curious about intermediate properties between faithfulness, fullness, and full faithfulness for a while. All of your examples are kind of motivated by ring theory. I wonder if you have had the chance or motivation to think about these properties in the context of, say, geometric morphisms in Topos theory.
Okay, thank you very much for the question. I don't know. We haven't yet considered Topos theory, but I think it will be interesting to focus on. But for the moment, I don't have an answer.
Thanks.
Oh, has anyone got a hand up online? No, it seems not. So let us thank. Take care again.
Thank you.